Welcome to the pre-recording of the first part of a tutorial on multiple double and multi-word arithmetic, scheduled to happen on Tuesday 10 June at the 2025 ADA Europe Conference on Reliable Software Technologies. So this first part is centered on a new ADA 2022 feature, uh, the big integers and the big reals. Okay, so here is the overview. Computers these days are very fast, so one needs to be careful about overflows and rounding errors that are happening. So I will, in this first part, at the beginning of this tutorial, kind of motivate why we may want to go beyond hardware arithmetic. So this tutorial is scheduled to be very self-contained. So in particular, you wouldn't really need to um, know all that much about arithmetic or about ADA itself. I will try to be keep it quite general at the very beginning. Okay, so beyond hardware arithmetic, so if we work with exact integers, we have a range of numbers, but often that is insufficient for correctness. I will give examples of that. Um, Software-driven or software-defined arithmetic carries a cost overhead. So computers have become fast, and actually they have become a lot faster in the sense that every computer is a parallel computer. So this tutorial is split up in 4 parts. The first part, that is the focus of this pre-recording, is on the big numbers introduced in ADA 2022. And I will use this somehow as a reference to introduce multiple double arithmetic in the rest of this tutorial. So I have a GitHub repository with some very simple examples. So this is a conference on software technology, so a conference also for programmers, and I learned through programming. So what I'm going to introduce in this tutorial, this is based on some very basic coding examples. 4 parts in this tutorial. So after the big numbers, I will define the multiple doubles, which have the benefit that you still exploit the floating point arithmetic as is available in the hardware. So computers are still optimized for floating point arithmetic. Nevertheless, the cost overhead can be significant. And in the third part of the tutorial and also in the last part, I will mainly focus on how to organize the computations, how to use parallelism and vectorization. Okay, so reliable computing. So has this already not been done? So if you do a computation in floating point arithmetic, should there not be automatic tools that take care of this? And the answer is, of course, yes. And the point of this first part of the tutorial is to explain how ADA programmers can solve this. But there is also a recent preprint. So when I was preparing for this tutorial, I have a daily emailing of the archive preprint server, and I came across this paper just to indicate that this is still an active area of research, and the paper is also relevant for the multiple double arithmetic. Okay, big integers. So my starting point for working with big integers. So I have programmed in Ada for about more than 30 years, but the big integer type was also for me new. So I went to the website learnadacore.com, which is a very excellent starting point for learning all kinds of things about Ada. So when I took the first example there, so 2 to the power 256, one can write that long number with essentially one instruction, the put line, um, after including the ada.numerics.big numbers. So the big integer data type is available in the big integers of the big numbers, part of the numerics library of Ada. Fine. If you see an example, one should always ask, is this actually correct? And this is where the binary and hexadecimal format is interesting, because 2 to the power 256 is defined as 1 and 256 zeros in binary. So to verify this, so this is an extension of our first program, which I called Hello Big Integers in the GitHub repository, that will print the 2 to the power 256 in base 16. So you see a 1 followed by 64 zeros, and in binary you see 256 zeros. So this number, this very large number, can be represented correctly with the big integer type. So just to refer back to the hardware integers, so they are either 32-bit or 64-bit, which are the most commonly formats. And then with 64-bit, you are of course limited to 2 to the power 62 for the signed integers. You can go more, longer, twice as much for the unsigned integers. And then there is also the long integer type, which is supported, which is 128 bits. But that's how far hardware can bring you. Okay, a first illustration. Why would you actually need the big integers? Well, if you start to count something, and here is an example of similar thing that you count, you construct the Fibonacci numbers. It's actually very, so again, this refers to the fact that computers are extremely fast. If we are computing Fibonacci numbers, then quite quickly we get to numbers that can no longer be represented correctly. So here is the definition of the sequence of Fibonacci numbers. We start with 0. So in a program, we convert 0 to the type big integer. We also convert 1 to big integer. And then we're going in a sequence, we're going to add the two previous numbers to make the next number. So this is a very simple loop where we essentially do only one addition. So the 1000 Fibonacci number takes 998 additions. There you see the long number, and we see that this output has 210 decimal places. So the numbers can go very quickly. Another traditional example is to compute factorials, 1 times 2 times 3 times 4, and then you will see that you will quickly get to huge numbers. So this is increasing exponentially. So big integers are an addition to Ada 2022. You compile the program with the GNU Ada compiler with the flag -GNAT 2022. Okay, floating point numbers now. Floating point numbers are important because as numbers are starting to grow, at some point we may be interested in the magnitude of the number. So with the Fibonacci numbers, we may be interested to know that, well, there are 200 decimal places, 210 decimal places. So this is a number 10 to the power 210. So in some sense, with floating point arithmetic, we will still be able to capture the magnitude of the number. Okay, so I wanted to make this tutorial self-contained. So if it has been a very long time that you have used floating point numbers, then a floating point number in the hardware consists of one sign bit, so that's typically the leading bit. Then we have exponents, and then we have a fraction. So there is a tuple, which is one sign bit, a number of exponent bits. So when one looks at floating point numbers in the scientific notation, one reads these numbers from right to left. So one first actually looks at the magnitude of the number. So we have a floating point representation. And while there are many possibilities, many numbers that can be encoded that way, one will already there often have a representation error. Okay, so what is predefined? So in Ada we have the predefined float, long float, and long float. They are also typically referred to as single precision 30-bit numbers, 64 or double precision number, and then there is the long double that gives you 80 bits. So the sign bit remains invariant. The exponent grows, so this has consequences for when overflow, or underflow is often very silent, but overflow will result in an error. The fraction determines how accurate you can represent your numbers. So typically in scientific computing, we work with 64-bit floating point numbers or doubles. 11 bits in the exponent, 52 bits in the fraction. In some sense, we have often a little bit more because the first bit in the fraction is always 1. So in some sense, this might not be represented explicitly. Okay. There is the number line. So the distribution of the numbers, what is here with this very simple example indicated, is that if you have, say, a very simple number system that has only 2 bits in the fraction, and where also your exponents are limited to -1, 0, 1, and 2, so you only have 4 bits in your exponent, then actually you can start to list explicitly all the numbers that you can make in this number system. So there are only 16 numbers. So the point of this slide is that in the number line, so the highest number is only 3 here for this example. So as you get with higher numbers, then the absolute error, the absolute representation error, turns to be a lot larger. So, and this is to indicate that when you work with floating point numbers, it's best to scale the numbers in the range 0 to 1, where the representation errors are a lot less than farther away. Okay, machine precision depends on the size of the fraction. It is defined as the smallest positive number that you can add to 1 and still make a difference with 1. So it's important to note that if you have an epsilon number, an epsilon that is smaller than the precision, then actually when you add that number to 1, you actually get 1. So the left of this assignment is 0, while the right of this assignment is non-zero, is that epsilon. So the order in which you do your computations in floating point arithmetic matter. Okay, so for different precisions, we have about 7 bits in single floating point, 7 decimal places accurate with single floating point precision. This kind of doubles in double precision. You can go up to 15, 16 decimal places. With long double, we have 20 decimal places of machine precision. Okay, the smallest and the largest number that you can make. So this is important to avoiding overflow. So we have that with single precision. We have a range of the exponents going, so we have 8 bits in the exponents. We can range between negative 126 and plus 127. This has consequences then later for multiple double arithmetic. If we're going to use the sequences of doubles, we will still be limited by the exponent range. So that is often a reason why you may want to consider doubles over single precision, and even consider long double. There are some special values. We have the negative infinity and plus infinity that we can represent with the highest exponent, but then a zero fraction. A fraction that is entirely zero is also actually not normalized. Also, when the exponent is zero, then you can make numbers that are not normalized. Okay, this is a very quick refresher or very quick introduction on the characteristic of the hardware floating point arithmetic. Okay, as an Ada programmer, you can extract the fraction and you can extract the exponent. So the long integer is predefined in Ada, but actually I prefer often to work with the shorter name, integer 64. I've left the long float. Sometimes I prefer also the shorter name double or double float. So we take the number 0.1. We can extract the fraction and the exponent via these attribute notations, the apostrophe and then fraction of the type with as argument the number, here in case the 0.1. We can go one way, extracting the fraction and the exponent. We can go the other way, given a fraction and giving a particular exponent, we can make a double number. This is interesting to take the fraction and convert that fraction to a 64-bit integer, which has actually only 52 bits that are meaningful. That is important when you work with multi-word arithmetic later. Okay, but what I want to do with this example 0.1 is to indicate that 0.1 has a binary expansion that is infinite. So you can't really represent the 0.1 correctly, which is a little bit a surprise for us, typically thinking in the decimal. We know that 1 over 3 is represented as 0.33333, an infinite sequence of 3's, but that 0.1 cannot be represented correctly by the hardware floating point numbers is some kind of is not entirely intuitive, may lead to surprises. So that means that as soon as you already work with 0.1, which looks a very nice and innocent number to us, you are already introducing an error in your computations. So, and as computers are extremely quick, these initial errors may actually blow up on you. Okay, in some sense, this is motivation to work into the big reals. And what I discovered, and this I didn't actually know this before when I was preparing this tutorial, is that the big real data type, which is also part of the big numbers now, that is actually equivalent to working with exact rational arithmetic. So I'm going to illustrate this with this example 1/10. So we can define 1/10 via a long float. That was the x that we were using. But we can also define the big real as the quotients of 1 over 10. So 1 and 10 are both integers which can be cast quite quickly, converted quickly into big reals. And with this example, I will demonstrate that if you compute the error, so in some sense what is very important here, if you want to avoid representation errors, you should not use the conversions, because that takes the floating point representation of 0.1. So the z is the big real version of the 64-bit floating point version of 0.1. And even though you work with big reals, you will have your floating point representation error. So the code here, when you execute it, it produces this output. We defined the y as the big real of 1 divided by the big real of 10. And if you print it out with 32 decimal places, you see indeed a 0.1 followed by all these zeros. What is nice is that you can ask for the numerator and the denominator. So this actually indicates that um, when I looked also at the code via GitHub, you can see there is the source code of the open source GNU Ada compiler. You can actually see the definition of the big reals, which is a wrapper which is built on top of the big integers. And here you also see the difference. So we can subtract x from y. You see the representation error. So what is important is to keep in mind that you have to define 0.1 or 1 over 1 divided by 10 via the numerator and denominator construction and not as the conversion. Okay, what are the applications of this? Well, I give you 3 applications. So we can work with rational approximations of pi by taking larger and larger number of bits of the fraction of the floating point approximation of pi. In some sense, it's kind of a warning also. It's kind of big reals can give you the illusion that you work exactly with exact rational arithmetic, so you should not worry about any errors. But of course, you start with a rational approximation of pi, and pi cannot be represented by an exact rational number. In many applications, you may have a need to solve 2 by 2 linear systems, and here is a benefit if you start with rational inputs. I will show how to make a random rational system. You can actually solve it exactly. And if you are interested in root finding, one can run Newton's method, which converges quadratically, which is very beneficial, which converges quadratically to regular roots. And one can actually quite quickly compute very accurate approximation of square roots. So square roots are kind of in between the rationals and the series reals. They are algebraic numbers. Okay, so here is the application of conversion, where you take the double precision approximation for pi, which is predefined in the numerics of Ada. You convert it to a big real, and then you can print out the numerator and the denominator of this big real approximation. So this shows you a very long number, and perhaps this might not be that suitable to work with. What you can do is you can take the fraction and select the number of bits you need. So I've indicated the getting of the fraction and the conversion to 64-bit integer. So you can see the sequences. So I only printed out the different. So if there are 0 bits, nothing will change. So we start with 25 divided by 8. And then the next rational number is 201 over 64. And you see we have a sequence of when we take more and more bits in our fraction in the double precision floating point approximation of pi, we get longer and longer rational approximations for pi. So this is a first built-in algorithm in the conversions. So one can select bits. So you select the fraction, you convert the fraction to an unsigned 64-bit integer, and then with the AND operation, where the mask is consisting of the ones that you want to select, you can actually select with the AND operation the number of relevant bits that you want from the fraction. And then converting to big real, asking for the numerator and the denominator will actually give you an approximation for pi. Okay, the second application, the solving of 2 by 2 linear systems. And for this I was motivated by applications from computational geometry, where you consider configurations points in the plane. So you have to intersect line segments or lines. How is this done? Well, you have two linear equations, and this linear system will have a unique solution when the determinant is different from 0. So this determinant will show up in the denominator of the solutions. And Cramer's rule takes the coefficient matrix and replaces the first column by the right-hand side vector for the first component, and then it replaces the second column by the right-hand side vector if you want a second component. Okay, here is a random example. So I generate random digits, positive numbers for the denominator. I don't want to pick 0, so 1 up to 9. And then for the numerator likewise. And then you see you compute the determinant, so it's not 0. If you are very unlucky, so we have many choices, but if the random number generator, if you would run this many times, you're going to go through all possibilities, and it could so happen that the 2 rows and the 2 columns would be linearly independent. So for a safe program, you always check first on whether the determinant is 0 or not. If it's not 0, then you can apply Cramer's rule. And here you see already one interesting example. I started out with single digits as the inputs for both the coefficient matrix and the right-hand side vector. And you see that I have 3-digit numbers in the solution. So the numbers are starting to grow. So Cramer's rule can still be applied for 3 by 3 systems, but I wouldn't go much beyond that. Even with the exact rational arithmetic, if you start with a very small system, by that I mean small numbers, single-digit numbers, with exact rational arithmetic, your numbers are going to blow up. So this is already visible in this very simple example, which always should verify that when you compute b minus a of x, that gives you the residual, that you get the 0 factor back. Okay, so here are the steps in the code. So I define a matrix range, so 1, 2, because I'm dealing with 2 by 2. There is the array that we define with the matrix structure. We have one-dimensional arrays for the right-hand side vector, and for the solution vector. And then we have two-dimensional arrays for the coefficient matrix. And then you define functions to implement Cramer's rule and also to compute this residual vector. So this is a relatively short program that will guarantee you the exact solving of a 2x2 linear system, provided that the determinant is different from 0. Okay, third and last application is the computation of square roots. So a square root is a solution to a very simple equation, so x squared minus n. And we can start the computation at the square root of n. By that I mean actually the square root of n, the long float approximation, because otherwise there is no big real square root. But it's very quickly defined. So you run Newton's method and you will observe quadratic convergence. So the number of correct decimal places doubles in each step. So already, and that was also, this is parallel to the Fibonacci numbers, with relatively very few computations, you get a lot of data, you get a lot of decimal places. So here you see the start of the code. Actually, this is almost the entire code. I start with the square root. The SQRT is predefined in the numerics, and that is from the initial approximation for this iterative method. So in a way, there is only one formula there, but we need to have a stop criterion. So 100 is kind of overkill, except if your tolerance is very, very small. But this converges quadratically. Typically only 4 or 5 steps are required if you need 32 decimal places, if you want to double the precision, for example. Okay, if you want to take the square root of 5 up to 255 decimal places, then here is what you get. This is also to indicate that also here for this example you actually get already large numbers. Okay, this gives kind of a first introduction of the big numbers that were introduced in ADA 2022. There is kind of the trade-off. If you want to work with exact arithmetic, and that is actually what the big numbers are doing, then actually you will incur expression swell. So the numbers will actually grow too large, and computers still have only finite memory. So you will run into those limitations. And if the end result is also large, there's actually not that much that you can do. Now, in many applications in science and engineering, so one can keep working with limited precision, provided that you kind of have good algorithms that keep the round off bounded and that are not too sensitive to representation errors. So there is the field of symbolic numeric computations where you try to combine the best of both worlds. But it's important to know that sometimes there are no good algorithms available, and numerical algorithms in the sense that you will have to work with exact computations or extended precisions, which will often not be possible to conclude. Okay, finishing this first part at a positive note. So I indicated that um, there is actually an automatic way to verify the correctness of your results. So big number arithmetic is possible in Ada. So you can actually write your programs that are can be running in two modes. So you can have one algorithm that is generic, that has the number type as a generic. And once you instantiate your code with the proper big number, and then also with the hardware arithmetic. And similar like running your program in debug mode, and you run your program in verification mode, where you would use the big numbers and where you could kind of see what are the limits and which you can still trust your code. So this leads to an automatic verification of floating point arithmetic. Okay, I'm at the end of the tutorial. Somehow as a summary, so I have 4 exercises. So these are kind of the exercises which kind of invite you to experiment with the big numbers. So I've introduced the Fibonacci numbers. So the Lucas numbers are very similar. Instead of pi, you can take the transcendental constant e, and also that also is a number that actually doesn't have a finite representation. Very useful for continuous compounding of interest. Kramer's rule is defined for 3 by 3 linear systems, so you can play with that, and there you will actually experience even more the growth of the numbers, but it will still be doable. And similarly to computing quadratic square roots, that we have a quadratically converging algorithm, you can work with x to the power 3 minus n, and that equation will give you cube roots. Okay, so this is the first part of the tutorial. First part in a half-day tutorial. The next part will be on the definition of double-double arithmetic and multiple-double arithmetic in general.